Arrow Lake is Intel's revolutionary new processor for mainstream desktop, featuring new PEcores and eCores, disaggregated tile-based 3D Foveros packaging, an integrated NPU for AI acceleration, a next-generation uncore, DLVR power rails, and so much more.
In this video series, I have a closer look at Arrow Lake and the performance tuning and overclocking opportunities. I have a look at the compute, the memory subsystem, and the data fabric. In this video, we're having a look at overclocking and undervolting the Arrow Lake PEcores.
The Arrow Lake PEcores are located on the compute tile. It shares the tile with the eCores, the ring, and the caches. An Arrow Lake S processor can have a maximum of 8 PEcores, like on the Core Ultra 9 285K. The PEcores feature the Lion Cove microarchitecture, similar to Lunar Lake. Unlike any previous Intel Core architecture, the PEcores do not have hyperthreading.
The clocking of the Arrow Lake PEcores is very similar to previous architectures. We have a reference clock that gets multiplied by a CPU ratio to get the ultimate operating frequency.
The 100 MHz reference clock frequency is generated internally by the CPU PLL. This clock affects all IP blocks in the compute tile, including the PEcores, the eCores, and the ring. This PLL can be linked to the SoC PLL when you run in synchronous mode or work independently if you run asynchronous mode. You can configure the CPU BCLK frequency between 40 and 1000 MHz. In the Asus ROG BIOS, you can configure the CPU BCLK frequency in the AI Tweaker menu by first setting AI Overclock Tuner to anything else than auto. Then you can switch between asynchronous and synchronous mode by adjusting the BCLK mode option.
The reference clock is then multiplied by a CPU ratio to get the operating frequency. Each PEcore can run at its individual frequency.
The effective PEcore CPU ratio is determined by 3 key inputs: the turbo ratio limit, the PerCore ratio limit, and the core minimum ratio.
Let's have a look at these technologies. Generally speaking, there are 2 ways to set the CPU frequency of an Arrow Lake CPU: sync all cores, or by using the turbo ratio limit configuration.
Sync all cores sets a single fixed ratio applied to all cores. This is the historical method of getting a static overclock. Turbo ratio limit configuration allows us to modify the default Intel frequency specification and configure a dynamic overclock. On the Core Ultra 9 285K, the PEcore turbo ratio limit starts from 37x, which is the same as the advertised PEcore base clock frequency. By default, the PEcores of this SKU can clock up to 5.7 GHz for up to 2 active PEcores and 5.4 GHz for up to all 8 active PEcores. We can configure 8 different scenarios, from 1 to 8 active PEcores. Each scenario is associated with a turbo ratio limit. There's also a fixed logic, ensuring the ratio for scenario N is higher than the ratio for scenario N plus 1. For example, we can create a scenario where 1 PEcore boosts to 5.8 GHz, 5 PEcores boost to 5.6 GHz, and all 8 PEcores, when they're active, boost to 5.5 GHz. The PEcore turbo ratio limit configuration works independent from the eCore configuration. So even when all eCores are active, if only 1 PEcore is active, then the frequency will be 5.8 GHz according to our example. PerCore ratio limit allows you to set a maximum CPU ratio for each PEcore individually. It's an extension of the Intel Turbo Boost Max 3.0 technology introduced in 2016. It acts independent from the turbo ratio limit, meaning that when you set a PerCore ratio limit, the PEcore will be restricted even if the turbo ratio limit would allow for a higher boost frequency.
The PerCore ratio limit plays a very important role in Arrow Lake PEcore overclocking, not just because it's also defining the final VF point of every PEcore's VF curve, but also because a lot of other ratio tuning technologies reference the PerCore ratio limit.
In the Asus ROG BIOS, you can configure the PEcore ratio limit via the AI Tweaker specific performance core submenu.
Thermal turbo, or previously known as thermal velocity boost, is an Intel technology that clips the turbo ratio limit based on the operating temperature. It uses the same mechanism like OCVB, which we'll cover later in this video.
The principle is simple. When the operating temperature exceeds a predefined threshold, the turbo ratio limit will be clipped. In the example of the Core Ultra 9285K, we find that the turbo ratio limit is reduced by 1 bin when the operating temperature is over 70 degrees Celsius. To optimize the performance, we can disable this behavior in the BIOS. In the Asus ROG BIOS, you can configure the thermal turbo setting via the AI Tweaker Thermal Velocity Boost submenu by using the ETVB option.
The core minimum ratio is a brand new overclocking feature for Arrow Lake. It allows you to set a floor ratio for your PEcores. Note that it's still defined within the P states.
In other words, it's not a replacement for disabling C states in case you want to prevent core parking or cores going to sleep. In the Asus ROG BIOS, you can configure the minimum turbo ratio via the AI Tweaker Tweaker's Paradise submenu.
Granular ratios are also a brand new overclocking feature for Arrow Lake. This technology allows you to set CPU PEcore ratios in steps of 16.67 or 33.33 MHz. It's important to note that these granular ratios are configured in reference to the PerCore ratio limit, not the turbo ratio limit. And that's because behind the scenes, the granular ratio is actually downbinned from the PerCore ratio limit.
For example, let's say you set a granular ratio of 60.16. In that case, the PerCore ratio limit is set to 61x and downbinned by 5 steps of 16.67 MHz, which is 100 MHz divided by 6. That is important to keep in mind in case you're also using other ratio configuration technologies. In theory, you can set up to 255 downbin steps from the PerCore ratio limit. That can lead to some errors in the software reading. Let's say, for example, you set the PerCore ratio limit to 60x and then downbin 200 steps of 16.67 MHz. Then the operating frequency would be 2667 MHz instead of 6000 MHz. Fortunately, you'll find that most BIOSes give you a simple interface to set granular ratios. In the Asus ROG BIOS, you can configure the PEcore granular ratio via the AI Tweaker specific performance core submenu.
Overclocking thermal velocity boost, or OCVB, is an Intel technology that lets you define how the CPU should behave at different operating temperatures. It's not a new technology. We also saw OCVB on previous generation architectures, but the feature has expanded in functionality for Arrow Lake.
We can now configure the OCVB based on the PerCCP module or PEcore group. Perhaps an easier way to think about this is that the former adjusts the PerCore ratio limit and the latter configures the turbo ratio limit. The latter is functionality that's carried over from previous generations, whereas the former is brand new for Arrow Lake. In PerCCP module mode, each PEcore has 2 available OCVB points. Each point is defined by a target temperature and a number of downbins. Note that the downbins are cumulative, and thus the downbins from point B stack on top of the downbins from point A. For example, let's say we've set the PEcore 0 PerCore ratio limit to 60x, and then we set the PerCCP module OCVB point A to minus 2x at 50C, and OCVB point B to minus 2x at 80x. In that case, the frequency will be 6 GHz below 50 degrees Celsius, 5.8 GHz between 50 and 80 degrees Celsius, and 5.6 GHz above 80 degrees Celsius. The OCVB trigger point is the core-specific temperature. So even if all other cores exceed the PEcore OCVB temperature point, as long as that specific PEcore temperature doesn't exceed the target's temperature, it will not downbin. In the Asus RAG BIOS, you can configure the overclocking thermal velocity boost per CCP module via the AI Tweaker thermal velocity boost submenu by first enabling overclocking TVB and then setting OCVB configuration limit to per CCP module. In per PEcore group mode, each PEcore turbo ratio limit scenario has two available OCVB points, each of which is defined by a target temperature and a number of downbins. Note that the downbins are also cumulative, and thus the downbins from point B stack on top of the downbins of point A. For example, let's say we've set the turbo ratio limit for two active PEcores to 60x, and we set the per PEcore group OCVB point A to -2x at 50C and OCVB point B to -2x at 80C. In that case, when two PEcores are active, the frequency will be 6 GHz below 50C, 5.8 GHz between 50 and 80C, and 5.6 GHz above 80C. In the Asus RAG BIOS, you can configure the overclocking thermal velocity boost per PEcore group via the AI Tweaker thermal velocity boost submenu by first enabling overclocking TVB and then setting OCVB configuration limit to per PEcore group. One last thing to mention is that, for now at least, the temperature point is 5 degrees off. By that I mean that if you set the OCVB point to 55 degrees Celsius, it actually kicks in at 60 degrees.
AVX Ratio Offset allows us to reduce the CPU PEcore frequency when workloads use AVX instructions. It does this by referencing the PerCore ratio limit, not the turbo ratio limit.
AVX ratio offsets are useful to achieve maximum performance for both SSE and AVX workloads. The AVX ratio offset behavior is managed using a frequency licensed base approach. In theory, there are 4 frequency levels, ranging from L0 for SSE to L3 for AMX workloads. However, on Arrow Lake, we only have licenses L0 and L1, since it doesn't support AVX 512 or AMX instructions. Each level is associated with particular instructions ranging from the lightest to the heaviest. Each level is then also associated with one specific ratio offset. As a rule, the ratio offset configured for a given frequency license must be equal to or higher than the preceding frequency license. When the AVX ratio offset is triggered, the PerCore ratio limit is temporarily reduced by the number of defined AVX ratio bins. In the Asus RAG BIOS, you can configure the AVX ratio offset via the AI Tweaker AVX related controls submenu.
The voltage regulation of the PEcores on Arrow Lake is significantly different than on prior generation Intel processors, and that's because of the introduction of the DLVR. The DLVR technology allows for the PEcores to run at much lower voltages, but it still relies on a dynamic external motherboard voltage regulator as the voltage source.
Each PEcore has its own VF curve, which is defined by up to 9 VF points. The first 8 VF points are factory fused, and the last point is mapped to the OC ratio. Here is the PEcore VF curve for my specific Core Ultra 9 285K. The voltage is about 725 mV at 800 MHz and then increases to 1.17 volt for VF.6 at 5.5 GHz, ultimately ending at 1.313 volt for VF.8 at 5.7 GHz. 5.7 GHz is the default maximum turbo frequency for the PEcores. That's only the 2 favored cores though. The other, non-favored PEcores can only boost up to 5.5 GHz. That said, all PEcores have a VF curve up to 5.7 GHz. So, if you set the non-favored cores to 5.7 GHz, they'll still be running the appropriate factory fused voltage. In the Asus ROG BIOS, you can find an approximation of the PEcore's VF points, and thus the VF curve, in the AI Tweaker Performance Core VF Point Offset submenu.
Advanced voltage offset, better known as the VF points, is available for every single PEcore in your Arrow Lake CPU. There are a total of 9 VF points available for each PEcore, 8 of which have a predefined ratio. This ratio is the same for every PEcore.
The final VF point is mapped to the OC ratio, which is the PEcore per-core ratio limit. If you use granular ratios, keep in mind that those are downbin from the next full ratio. In other words, the OC ratio can never be a granular ratio. You can set a negative or positive voltage offset for each of these VF points and for each of the PEcores. The final OC ratio's base voltage will be the user-configured adaptive voltage. In the Asus ROG BIOS, you can configure the PEcore VF points via the AI Tweaker Performance Core VF Point Offset submenu.
To safeguard the processor, Intel has imposed strict voltage limits for the PEcores. This voltage limit prevents the PEcore from requesting higher voltages from the PCU.
By default, the voltage limit for the PEcores is 1.513 volt, but this can be increased to 1.61 volt under ambient conditions. When the temperature is below 10 degrees Celsius, you can further increase the voltage limit or disable the limit altogether. If you try setting the limit above the approved limit, the PCU will automatically adjust it to the highest allowed limit. If you disable voltage limits and the temperature is above 10 degrees Celsius, the CPU will operate in safe mode and limit the frequency to 400 MHz. For DLVR powered IP blocks like the PEcore, in theory, you can also change to PG mode or Powergate mode to override the voltage limit and set any voltage you want. But of course, motherboard vendors can implement their own voltage limits for the voltage regulator.
Thermal velocity boost voltage optimizations is an Intel technology that adjusts the operating voltage according to the operating temperature. Basically, the lower the temperature, the lower the voltage. When you're trying to manually tune the voltages, it's prudent to disable this technology.
When the voltage optimizations are enabled, we can use hardware info to track the CPU VID request as the CPU is heating up. I've collected data for the Core Ultra 9 285K to illustrate this behavior. As you can see from the data, with the PEcores at 5.4 GHz, the operating voltage is 1.237 volt when the temperature is below 50 degrees Celsius. However, it increases to nearly 1.3 volt when the temperature approaches 100 degrees Celsius. A regression analysis tells us that the operating voltage changes 1.1 millivolt for every change in degrees Celsius. In the Asus ROG BIOS, you can enable or disable the thermal velocity boost voltage optimizations via the AI Tweaker Thermal Velocity Boost submenu. The external VCC motherboard voltage regulator, or NVMe, provides the input voltage for the individual PEcore, ECore clusters, ring, last level cache, and ECore L2 cache. Each PEcore, ECore cluster, and ring has an individual digital linear voltage regulator, or DLVR, between the VCC voltage rail and the IP blocks. That means each of the blocks can operate at its own voltage. The VCC Core is the DLVR powering an individual PEcore. The DLVRs can also be bypassed. In that case, the IP blocks are running in so-called Powergate mode, or PG mode. In PG mode, the VCC voltage rail directly powers the IP blocks, and they all share the same voltage. That's similar to how previous generation desktop architectures worked.
The default mode of operation is DLVR mode, so let's explore that first.
Based on the VF curve, the PEcores request an operating voltage using the ISVIT protocol from the CPU Power Control Unit, or PCU. The PCU, in turn, configures the VCC voltage rail and the individual VCC Core DLVRs. There's two ways to configure the PEcore voltage. adaptive mode, or override mode. Adaptive mode is the standard mode of operation, which relies on the factory-fused voltage frequency curves we discussed before. In override mode, we specify a single static voltage across all ratios. It is mainly used for extreme overclocking where stability at high frequencies is the only consideration. We can configure override and adaptive modes directly in the PCU by specifying a target voltage and a voltage offset for each mode. In adaptive mode, the target voltage is mapped to a PEcore's OC ratio. Each PEcore has its own OC ratio, which is defined by the PerCore ratio limit. This also matches the PEcore VF.9. You can configure the adaptive voltage and the OC ratio to any value. However, multiple rules enforce what ratio and voltage is actually set. Rule number 1. The voltage set for a given VF.N must be higher than or equal to the voltage set for VF.N-1. In the case of the PEcore, it means that the voltage for the OC ratio, matched to VF.9, must be higher than or equal to the voltage for VF.8. This can be a little bit strange because you can program the OC ratio to any value, including lower than 57x. For example, let's say you set the PEcore ratio limit to 52x and the adaptive voltage to 1.1 volt. In that case, VF.9 will be programmed to 52x at 1.1 volt. However, the actual frequency will be 5.2 GHz with 1.313 volt, as that's the voltage for VF.8. Rule number 2. For ratios between the OC ratio and the next highest factory-fused VF point, the voltage is interpolated between the set adaptive voltage and the factory-fused voltage. Let's say we configure the PEcore VFOC point to 60x and 1.4 volt. The target voltage for PEcore ratios between 57x and 60x is now interpolated between the factory-fused voltage for 57x and the set adaptive voltage for 60x. In the Asus ROG BIOS, you can configure the PEcore DLVR voltage in the AI Tweaker menu. You can configure in adaptive, manual, and offset mode.
2 additional side notes about using adaptive voltage.
First, the adaptive offset is applied across the entire curve. So if we set a plus 100 mV adaptive offset, the operating voltage for all frequencies between 8x and the OC ratio will be increased by 100 mV. Second, any adjustments made to the VF curve is still subject to the aforementioned rules for adaptive voltage. That includes the adjustments for VF points. For example, let's say the PEcore 0 voltages for VF points 7 and 8 are 1.2 and 1.3 volt respectively. If I configure a minus 150 mV offset for VF.8, then the effective voltage will be 1.2 volt, not 1.15 volt, because adaptive voltage rule number 1 is enforced.
Intel PerCore voltage is an Intel technology that allows you to set an individual voltage target for each PEcore in your CPU. I do have to note that this technology is only available in DLVR mode.
Just like in DLVR mode, you can configure the PerCore voltage in adaptive mode and override mode, specifying a voltage for the defined PerCore ratio limit or across the VF curve respectively. The PerCore voltage implementation for Arrow Lake is slightly different than prior platforms, as each PEcore now has its own OC ratio. Functionally, that means each PEcore's PerCore voltage is mapped to its PerCore ratio limit, and thus also serves as the base voltage for VF.9. The standard rules for adaptive voltage mode still apply for each PEcore. As a consequence, it means that each PEcore's VF curve is truly independent as voltage interpolation is done for each PEcore individually. Let's say we configure the PEcore 1 VF.9 to 60x and 1.4 volt, and we set PEcore 2 VF.9 to 61x and 1.45 volts. The target voltage for PEcore 1 ratios between 57x and 60x is now interpolated between the factory-fused PEcore 1 voltage for 57x and 1.4 volt for 60x. For PEcore 2, the ratios between 57x and 61x are interpolated between the factory-fused PEcore 2 voltage for 57x and 1.45 volt for 61x. In the Asus ROG BIOS, you can configure the PerPecore DLVR voltage in the AI Tweaker specific performance core submenu. You can configure it in adaptive, manual, and offset mode. In Powergate mode, all the DLVRs tied to the VCC IA voltage rail are bypassed, and the connected IP blocks are powered directly by the VCC IA voltage rail.
Powergate mode is basically how the VCC IA voltage rail worked on prior generation Raptor Lake processors. On Arrow Lake, it works as well, but it's a little bit complicated.
To make a long story short, when the PEcores, eCores, and Ring request their voltage to the CPU PCU, they account for a ton of other compensations, including voltage droop, DLVR efficiency, AVX garband, thermal velocity boost voltage optimizations, and so on. The result is that the actual voltage provided from the VCC IA voltage rail to the DLVRs is relatively high. For example, here are the voltages with the CPU at stock voltage and frequency running an all-core light workload. We can interpret this as follows. The PEcore, eCore, and Ring request a voltage to the PCU to ensure they'll run at 1.15, 1.05, and 1.1 volt respectively. The PCU then adds compensation for the load lines, CEP, TVB, AVX, ACLL, DLVR efficiency losses, and so on. At the end of the calculation, the PCU determines the VCC IA voltage rail should provide 1.43 volt input voltage to the DLVRs. If we were to switch to Powergate mode, but maintain the same mechanism for calculating the required voltage, then the VCC IA voltage rail would effectively provide 1.43 volt to the PEcores, the eCores, and the Ring. That's obviously way too high for the target frequency and would quickly result in an overheating system. But this would be how voltage was configured on previous generation Raptor Lake processors.
Fortunately, there's another way to approach Powergate mode. Ignore all the isFID requests and calculations and program the VCC IA voltage regulator directly over PM bus. This effectively gives us direct control over the VCC IA output voltage.
This approach is a very traditional way of overclocking, whereby you set a fixed output voltage and then use an appropriate VRM load line setting to reduce the operating voltage in higher load scenarios. Let's have a look at an example and compare Powergate and DLVR in Cinebench R23. If we set 1.35 volt with load line 6, then the effective voltage under load is 1.26 volt. That's about 150 millivolt higher than with DLVR. Despite the higher voltage, the temperature is only 7 degrees Celsius higher than when we run with DLVR enabled. If we set 1.3 volt with a load line of 4, then the effective voltage under load is 1.15 volt, which is very similar to what we get when we use DLVR. Despite the almost identical voltage, the temperature is 7 degrees Celsius lower than when we have DLVR enabled.
The bottom line on DLVR versus PG mode is that DLVR seems to offer us better temperatures and power consumption in low load scenarios, whereas PG mode seems to offer us better temperatures and overclocking headroom in high load scenarios. And that's because there's a power loss associated with using a linear voltage regulator. That power loss, due to DLVR efficiency, translates into heat, and that heat or that extra heat will eat into the thermal budget of our thermal solution and ultimately reduce the overclocking headroom. How much power are we talking about exactly?
Well, the power loss across the linear voltage regulator equals the decrease in voltage across the DLVR multiplied by the total load. So in our example, with a voltage drop of 305 millivolt and a 160 amps load, the power loss is about 50 watts. And nearly all of that power loss will convert into heat. For high load scenarios, Powergate mode appears to offer better overclocking headroom because the operating temperature is lower. However, we cannot rely on the PCU to control the VCC output voltage because its calculations are too conservative. So it ends up overvolting too much. Therefore, the right way of overclocking using Powergate mode is to ignore the ISVID requests entirely and take direct control over the VCC voltage regulator. This also requires setting an appropriate VRM load line to ensure lower voltage in all core workloads. In the Asus ROG BIOS, you can switch between DLVR and Powergate mode for the VCC voltage rail in the AI Tweaker menu by configuring the CPU DLVR mode menu item. You can set the VCC voltage rail in the AI Tweaker menu by configuring the actual VRM core input voltage in manual mode.
The processor power consumption is governed primarily by the Turbo Boost 2.0 technology. Intel Turbo Boost 2.0 technology allows the processor cores to run faster than the base frequency if the operating conditions allow for it.
The Turbo Boost algorithm works according to an EWMA formula. This stands for exponentially weighted moving average. There are three main parameters to consider: PL1, PL2, and tau. Turbo Boost 2.0 technology has evolved over the past years to incorporate many power, thermal, and electrical performance limiters. To cover each of these parameters in this video would take up way too much time. Fortunately, Intel provides two performance profiles for the Arrow Lake SKUs, which configure all these settings for you. For the Core Ultra 9 285K, the Turbo Boost 2.0 profiles are performance and extreme. Should you wish to override the performance profiles, you can do so in two ways, either by manually configuring them in the BIOS or by enabling Asus Multicore Enhancement.
Asus Multicore Enhancement enables higher out-of-the-box performance by tuning some of the Turbo Boost 2.0 technology parameters.
Note that you can select an Intel performance profile and enable MCE at the same time. The effect will be that MCE overrides the most common Turbo Boost 2.0 parameters such as PL1 and PL2, but it will adhere to other limiters such as current excursion protection configured by the Intel performance preset. The Asus Advanced OC profile is a more elaborate, unleashed overclocking profile than multi-core enhancement, as it not only adjusts the major Turbo Boost 2.0 parameters, but also implements a lot of BIOS auto rules to facilitate overclocking.
Overclocking the PEcores is very similar to how it was on previous generation Raptor Lake. Do note though that the performance improvement from overclocking the PEcores is less impactful than it was with Raptor Lake. That's on the one hand because the PEcores no longer have hyperthreading, but also because the E-cores improved quite significantly both in frequency capability as well as IPC. So unlike previous generations, on Arrow Lake, it's actually not a bad idea to prioritize E-core overclocking over PEcore overclocking.
Let's compare the performance improvement in Cinebench R23, changing the P and E-core clock from 4.6 to 5 GHz. The performance improvement from overclocking the 4 E-core clusters is about twice that from overclocking the 8 P-cores.
The PEcore overclocking range is also a little bit limited.
While all P-cores could do 5.8 GHz, only a few could make it to 5.9 GHz. That was with a quick OCCT stability test, so I wouldn't expect this to actually work for daily overclocks. I also tried leveraging OCVB to achieve 6 GHz, but I couldn't quite make that work either. In an all-core scenario, I could achieve 5.7 GHz in a light all-PEcore SSD workload such as Y-Cruncher BKT. However, in a heavy workload like Cinebench, which uses AVX instructions that don't trigger the AVX offset, the maximum PEcore frequency is about 5.5 GHz. The undervolting margin seems to be pretty decent though. I could undervolt about 100 mV for the PEcores at 5.4 GHz in an all-core workload.